Welcome to the fourth lecture of design and analysis of experiment. We will continue with types of experimental design. Why it is not going? Okay. So, in last class we have completed up to general factorial design. So, by types of experimental design we mean that depending on the situation different kinds of experiments to be conducted and what are those experiment, those types of experiment which has scientific basis and designed scientifically we are discussed here. There are many more designs which are available, all will not be discussed, most commonly used things are discussed here. And accordingly in last lecture we have discussed up to general factorial design. So, now we will explain few more like 2 to the power k factorial design, 2 to the power k minus p fractional factorial design, the central composite design, and we will name some of the other special designs which will not be discussed here. So, you have seen that in general factorial design there are many factors, each of the factors having different levels. Not necessary that the factors will be at 2 levels only, the factors can be have different levels, like a factor can be, factor A can have A levels, factor B can have B levels, factor C can have C levels, like this there are several levels. For example, let it's okay. For example, let there are 3 factors A, B and C. Now, if A has A levels, B has B levels and C has C levels, then how many treatment combinations will be there? A, B, C. If we consider A equal to 5, B equal to 5 and C equal to 4, then this is 5, 5, 25 plus 400 different settings. Now, again each settings if we conduct 5 replications, so you have to do 500 experimental runs only for 3 factors. Now, if the factor is 5 or 10 or 15, so what will happen? So, the number of experimental runs will be huge, and as a result you might have not in a position to conduct experiments, because cost is a issue, time is a issue, resource is another issue. So, cost, time, resource, other type of resource, all those things putting together will make it impossible to conduct full factorial experiment, And if you think that there will be A levels of for A and B levels for B, C level for C, this. So, under such situation what you will do? Will you not conduct experiment? Yes, you can do experiment. You can reduce the levels, you can make some systematic leveling also, like you can go for 2 to the power k factorial design, where k is the number of factors and 2 2 is label, number of label for each factor. Okay. What does it mean? In our earlier example, factor A 3 labels low, medium and high, and factor B 2 labels type 1 and type 2 filter. Now, if we go by this principle or this method, then in this case k equal to 2, and what changes is required? We may not consider medium clutter. We consider low and high. Then this will also label 2, this is also of label 2. So, we have 2 factors each with label 2, and the design is 2 to the power k means 2 to the power 2 factorial design. Okay. For example, here you see that this is, this is factor A, this side, this one is factor B. Maybe this may be some suppose in a chemical reaction, this is the concentration, okay, and this is maybe the amount used, pound. So, let if the concentration is 15%, we denote by low, if it is 25%, let denote by high. So, either minus or plus. So, low minus, high plus. So, this is basically 2 labels. Here also, if the amount used, amount of material used is 1 pound, it is low. If it is 2 pound, it is high. This low is again minus, high is plus. This symbol, it is also 2 labels. So, then effectively you have 2 to the power 2 means 4 treatment combinations. First combination is this. This we are denoted by within bracket 1. This is your when factor A is at high, but factor B at low level, this we are denoting by A. Then this is a combination, a treatment combination or the independent experimental setting where A is at low level, B is at high level. So, this is denoted by B, and this is one where both A and B are at high level, this is denoted by AB. So, this kind of design is known as 2 to the power k factorial design. In 2 to the power k factorial design, please keep in mind that we have k number of controllable factors, and each of the factors are set to 2 labels, label low, high or minus plus or minus 1 plus 1, that way sometime we will use coding variables minus 1 plus 1, that we will discuss when we go for detailed analysis of 2 to the power k factorial design. Now, in this 3 factor case, if A equal to B equal to C equal to 2, then this is the design. So, this is 2 to the power 3 factorial design. What does it mean? We have 3 factors, factor A, factor B and factor C and factor B. We have 3 factor A, B and C, and each at 2 levels. So, this is k, this each has 2 levels. So, level this one low, high, low, high, low, high. You have how many treatment combinations or independent or distinct experimental settings? 8, 2 to the power 3. Here it is 4, 2 to the power 2, because 2 factors. So, 1 to 8. Now, what is the first one? When all are at low, all low, A at low level, B at low level, C at low level. When A at high level, other 2 at low level, this is A. When B high, other 2 low, so this is your B. When both A and B high, C low, this is the setting AB. When C at high, other 2 low, this is the setting, this one. These are we have already discussed. Now, when both A and C are high, B at low, this is the setting. Similarly, BC, similarly ABC. So, now if you have four factors each at two level, you have two different cube like this, where we can what we will do. So, here suppose another factor D is there, D at low this kind of, and then D at high another cube, we will make another cube for D at high. Okay, so if you have further that k equal to 5, so you cannot pictorially like this cubic representation, not possible for much higher level and not required also 3 level. So, this is known as 2 to the power k factorial design. So, what is the difference between 2 to the power k factorial design and general factorial design? 2 to the power k factorial design and general factorial design. In general factorial design, what do you observe? You observe that the factors having different levels, So, A with A level, B with B level, C with C level, and with 3 factor case, the total number of experimental runs will be A, B, C into n for 3 factors, n is the replication. But here what will happen? You require 8 into n, A, B, C equal to 8. Here what happen? If it is general factorial design, it will be A, B, n number of experiments, and total treatment is combination A, B, here treatment combination A, B, C. Now, if you go for 2 to the power k factorial design, here it will be 4 treatment combination and you require 4 number of experiments to be conducted with n replications. Here it is ABC treatment combination 8n total number of runs. Okay. So, now think of a situation. I don't know, it is so disturbing. Now, you see that even if you go for 2 to the power k factorial design, suppose there are 10 factors, k equal to 10, what will happen? You require 2 to the power 10 in distinct treatment combinations or other way distinct settings, which is 1, 0, 2, 4. Now, if you choose replication n, this is 1024 n. Even if you consider 2, this will be 2048. So many runs required. So, even if you have k number of factors each with 2 levels, when k is large, number of experimental runs will be very large also. So, that is why what happened, it may not be feasible many a times to conduct 2 to the power k factorial design given that k is large. So, under such situation, can you not do experiment with lower number of runs instead of 1024 n number of experiment runs? Will it be possible to make it maybe half of this, or maybe 1/4 of this, or maybe 1/8 of this? Is there any scientific basis? Can we go for this? All those things will be answered in 2 to the power k minus p fractional factorial design. So, in this class we will not go into details of the 2 to the power k fractional factorial design, how it is done, and also why it is accepted, the scientific basis and all those things. But for the time being we want to know what is this to the power k minus p fractional factorial design. Let us assume that you have three factors a, b, c, three factors a, b and c, and you are doing to the power 3 factorial to the power 3 factorial to the power k time and to the power 3 factorial design. You are basically accepting this. Then you require 8 number of independent runs, and if you use app replication it will be 8n, but you do not have that much money or that much resource, materials not available or operators not available, you cannot do this. So, then if I go for 2 to the power 3 design and if I do it, that means each of the vertex, all the settings you are considering for this cube. Instead of that, suppose you want to do 2 to the power 3 minus 1, that means 1 half of 2 to the power 3. So, that means 4 number of independent settings you will consider, or 4 treatment combination you will consider. Is it possible? It is possible. How it is possible will not be discussed now, we will be discussing in when we will be analyzing to the power k minus p factorial design. So, in this case my k is 3, p is 1. This is known as 1 half into 2 to the power k factorial design, fractional factorial design, fractional factorial design. So, then what are those 4 points here? 4 settings, this and this. Okay. So, question is that 4 independent settings or treatment combinations you have not chosen, 1, 2, 3, 4, this not chosen, this is not chosen, this is not chosen, this is not chosen. So, whether will it work or not? So, it will work because there are certain hypotheses or observations or experiences already known, or some rules and laws that are already known, which is supporting this type of experiment. One is the sparsity of effect principles. Sparsity of effect principle means, suppose you have many factors, large number of factors, k number of factors. This principle says that the main effect like A, B, C, D, all those things, and lower order interaction effect like KC2, this lower order interaction effect will become significant mostly, not the higher order. Okay. So, in that case what happened, simultaneously if we use the projection property, what is this projection property? Projection property says that a fractional factorial design at the higher level has many full factorial design, full means to the power k factorial design at the lower level. What does it mean? Suppose you do this experiment or this one. Now, for example, here we are considering which one? This one, maybe this second one, this one. Here, here, here and here. These 4 experimental settings you have chosen for experiment, others you are not chosen. Now, you have taken 3 variable factors A, B and C. If you project this to 2 dimensions like either AB or AC or BC, what you are getting? You see the projection is such that in the 2 factor level, this is full factor, full one. All the factorial points are having data. You have already conducted experiment there. Even though at higher level it is fractional, means some of the factorial points are not considered, but at one lower level here this is full. Similarly, here you see everywhere point is there, here also. So, that is what says that because of this projection property, a fractional factorial design at higher level will have many full factorial design at lower level. So, that means, if I am interested to know the main effects and interaction effects only, that means two-way interaction effects only, then this is enough, because here you will get A B and A B interaction, here A C interaction. So, this is possible to get. Okay. Then then another one is sequential experimentation. This is also supporting this fractional one. For example, suppose you have done this, what you have seen here, and you have analyzed the data. If you analyze the data, you will not be able, using this design, you will not be able to estimate all the effects parameters A, B, C, A, B, A, C, A, B, C, because some will be confounded with others, because there are not data points not available in the half of the independent experimental settings. So, that means A effect will be confounded with B C, B will be confounded with A C, C will be confounded with A B. Confounded in the sense, they the experiments is conducted in such a manner that they are both the effects were basically I can say taken together, both the effects taken together, and when you analyze and get the effect, you will get the confounded effect, the total effect of the two, not individual effect. So, suppose you want the higher order interactions also to be taken together, or some of the confounders also that you have to find out, and their effect also separately want to calculate. In that case, suppose you require another experiment to be conducted, then you will not do second fractional experiment, second experiment with fractional factorial design at all those Boolean, you will do the remaining points. So, if I go for one half fractional factorial design, then if I do two different time experiment, one with that some 4 points into the power 3 design, 3 and another 4 points into the power 3 that case. So, then if I merge the two data set together, you are getting full factorial to the power k factorial design for the three variable case here. So, that means, if you do another experiment, you have full data set for this. So, these are the reasons why we will go for fractional factorial design, and these the result will be used for screening purpose. That means, what are the factors affecting, what are the factors not affecting. For example, if I go for fractional factorial and A is confounded with B C, suppose while estimating we found that this effect is not significant, then none of the effect is significant, we can eliminate, may. Okay. So, this is 2 to the power k fractional factorial design. Now, another important design is there known as central composite design. For example, you consider a to the power 2 design, you consider a to the power 2 design. In this case, what you do? You will your settings, independent settings are this. These are nothing but known as factorial points. Factorial points. So, 4 independent settings, 4 different treatment combinations. Okay. Now, it may so happen that suppose if these are the operator, the actual operating situation, so may not be represented by this, because it is obvious, because what you will do ultimately, you know the process operating zone, and you try to find out the low and high value here, and here also low and high value. So, if that entire operating zone is this, so low and high value you are considering, but will the operator operates at low and high all the time. Rather, operator will be operating at a point which is middle of this. This is known as, most of the time production will be done at this level. So, then this is known as center point. So, if you have the experiment, you do experiment at this center point, then you have more information about the current operating situation and the resulting performance in terms of response variable. So, in order to capture that, we must go for another setting which is or treatment combination is, this is known as center, which here in this case we have treated as 0 0, but why 0 or plus or minus 1, these things we will discuss later on. Okay. We basically use some coding scheme. Here you see the 3 dimensional case, 3 variable case, 3 factors case. So, this is the center point. So, you in design the experiment, you have factorial points, you have central points. Central point usually talks about the current operating performance, current operating zone and resulting performance if you have data on it at this case. And another one is that, suppose you may think that only this low, high and center point is not sufficient to capture the totality. So, you may go for some other points called axial points. What does it mean? You may do experiment here, experiment here, experiment here, as well as experiment here, or here in this case, particular case, this one, this one, this one, this one, and first, second, and this is another one, this is another one. So, axial point means that from the center it is alpha distance apart here on the both the axis x1 and x2 axis. Now, what is this alpha? There are different ways to choose the value of alpha, but sole purpose is you get more experimental settings or more treatment combinations and you get more data. So, that this definitely rich data. If I have only factorial point, the data I have, and if I go for central point, the data I gather will be richer than the first one. Similarly, if I have this plus this plus this, it will be richer data than the previous one. Richer data means give more information. Okay. Now, how do you choose the axial point? That alpha value may be square root of k, where k is the number of factors. It is known as spherical central composite design, or k alpha may be 1 for cubical central composite design. Okay. There are some other designs also, for optimality point of view there may be some more issues that when you go for central composite design in detail, that time you will know. Okay. So, that means here what happened, you got something more. One is central composite design with central point only, central composite design with central and axial points, and this why you require more data, because you require better response surface. This is used in second order response surface. So, sometimes that is why this is known as also response surface design. What is response surface? Response surface means given the x and suppose factor a and b, how the y, suppose the y is behaving, how y is behaving. So, this is the y response. So, that means if my a is here and b is here, my response value will be here. So, you require, when you go for second order, that means the quadratic effect will be there, curvature effect, all effects will be there. So, as a result what happened, you require more number of parameters to be estimated. So, you require more data points, otherwise you will not be able to estimate many important parameters. So, in order to achieve this, central composite design is preferred and you get more data points. So, some other design like Latin square design, Greco-Latin square design, mixture design, placket Barman design, robust design, nested design, split plot design, so many design depending on the situation you have to use. For example, Latin square and Greco-Latin square design. So, in Latin square design, suppose it is a special kind of design where you require less number of experimental runs to be conducted, and then you will be able to accommodate the blocking variables there also. You require, suppose you require 2 factors, 1 blocking variable, go for Latin square. You require 2 factors, 2 number of blocks or 2 number of nuisance variable into the experiment, Greco-Latin square. Mixture design I already told you. Robust design is very important one, because robust design is, as I told you, that the product you produce that will be used under different users environment. Now, if your design is not robust, so that it can withstand all other nuisance or environmental factors in the operation where it will be used, so then it is not a good product. So, accordingly, robust parameter design in the area of quality engineering, Taguchi has introduced this one, okay, that cross state design and other designs are there. So, nested design, split plot design, and some more designs are also available. I recommend all of you to go through design analysis of experiments by D.C. Montgomery, and in different chapters all different types of designs are explained, not in any one chapter the way I explained today, but it is, as the experimental design is very important and the types of design is extremely important. So, you must know all those types, and before going for conducting any experiment, because if you know the different types and under what situation all those which experiment to be chosen, and then accordingly you will plan for experiment and get the experimental results when actually you do in practice. So, thank you very much. This is what the introductory part of experimental design related to the design analysis of experiment, and in next class I will start with experimental data and different kind of statistics and how do you compute all those statistics, and finally goes to probability distribution and different kind of sampling distribution, and then hypothesis testing. In maybe next 3 hours of time we will be discussing all those things. Do not miss any of those classes, because the quantitative nature or quantitativeness of these particular subjects will be understood from those lectures.